All right, welcome back to the deep dive. It's Monday, February 16th, 2026. And I was looking at the calendar this morning and I think we finally made it.
Made it, buddy, where?
Through the hype cycle. Remember
Sure.
2023, 2024. Every single day there was some new chatbot that could, write a bad poem.
Oh, I remember. The wow, it speaks English phase.
Exactly.
Exactly.
But that's over. We're not looking at parlor tricks anymore. We are squarely in the industrial phase of AI. And to prove it, we've got a monster of a document to get through today. It's the AI Tech Stack Panoramic Report for 2025-2026.
It's a dense one, for sure, but it's absolutely necessary reading if you want to understand what's happening.
It is, but honestly, it reads less like a software manual and more like a
Yeah.
blueprint for a totally new kind of civilization.
That's not really an exaggeration. I mean, the stack isn't just code anymore. What we're looking at today goes from the atomic level, literally physics and heat, all the way up to international law.
It's a whole ecosystem.
It's more like an autonomous system. We really need to stop thinking of AI as just a tool, something you open on your laptop. It's infrastructure, it's data, it's logic, it's laws, all kind of merged into one giant machine. And our goal for this deep dive is to take that machine apart piece by piece and really see how it works.
Okay, so let's grab the screwdriver. We have to start at the bottom, the physical reality. Because apparently in 2026, the biggest problem in AI isn't the code, it's the temperature.
Heat and bandwidth. Yep. Those are the two tyrants ruling the industry right now.
So let's talk hardware first. Layer 1. The report says the general-purpose CPU, the Intel or AMD chip that's been the brain of computers for 40 years, it's basically a second-class citizen now.
Oh, it's a sidekick. It's the one holding the flashlight while the superhero does all the work. We've fully entered what they're calling the Rubin era.
NVIDIA's platform, right?
Yeah.
Named after Vera Rubin. But here's something I didn't quite get. The report calls it extreme co-design. That sounds a little like marketing fluff. What does it actually mean?
It's actually a massive, massive shift in strategy. In the old days, you'd buy a CPU from one company, a motherboard from another, memory from a third, and you just bolt it all together. Extreme co-design means those days are just over.
So you can't just buy the chip anymore.
No. You're buying a Vera CPU, a Rubin GPU, and NVLink 6 switch, all basically welded together into one unit. NVIDIA isn't selling components, they're selling a computer.
That feels like a monopoly move. You're locking everyone into one single architecture.
It absolutely creates a moat, no question. But the engineers would argue it's necessary because of the speed. The stats on this thing they're absurd. Inference speed, how fast it thinks, is 5 times faster than the Blackwell generation from just a couple of years ago.
5x in 2 years is just wild. But the number that really jumped out at me, it wasn't even the speed, it was the memory bandwidth. HBM4, 22 terabytes a second. 22, I mean, can you even help me visualize that? What does that actually look like?
Okay. So think about it like this. Remember trying to drink a really thick milkshake through one of those tiny coffee stirrers?
Ugh, yeah, the worst.
Right. Your lungs have the power, that's the chip, but you just can't get the milkshake through the straw fast enough.
So the straw's the bottleneck.
Precisely. HBM4 is basically throwing away that stirrer and grabbing, a fire hose. 22 terabytes a second means the chip is never, ever waiting for data. It's being force-fed information as fast as it can possibly process it.
But this is where physics kicks in, right? You run that much power, that fast, through a tiny piece of silicon, and things get hot.
Extremely hot.
The report says a single server rack is now pushing over 100 kilowatts of heat. That sounds dangerous.
It is. I mean, for context, 100 kilowatt is enough to power a small neighborhood, and that's from one rack. If you tried to cool that with traditional fans, they'd have to spin so fast they'd sound like jet engines, and they still wouldn't move the heat away fast enough.
So air cooling is just...
Yeah.
It's dead.
Completely dead. It physically cannot do the job, which is why 84% of the market has moved to liquid cooling.
And we're not just talking about like little water pipes running through the back, are we? The report describes something called immersion cooling.
This is my favorite part of the modern data center. You literally take the entire server, rack electronics, cables, everything, and you dunk it into a bath of dielectric fluid.
Wait, hold on. You're submerging the computer, the whole thing.
The whole thing.
Doesn't that short it out?
No, because the fluid is non-conductive. It doesn't carry electricity at all, but it carries heat incredibly well. The fluid touches the chips directly, and as the chips get hot, the fluid literally boils on the surface of the silicon.
That is just bizarre.
It's so efficient. But just imagine walking into a data center in 2026. 2 years ago, it was this deafening roar of fans. Now, it's silent. All you hear is this gentle bubbling sound from the tanks. It's like a library full of aquariums.
A library of boiling aquariums. That is a very sci-fi image. But okay, you've got these super hot, liquid-cooled brains. But a brain in a jar is useless if it can't talk to other brains.
Correct. And that brings us right to layer 2, the nervous system, networking.
This seems to be where the bottleneck moved. We fixed the chip speed, we fixed the memory straw, but now the problem is connecting them all.
Right, because modern AI isn't one computer. It's 10,000 GPUs trying to act like one computer. And if the cable connecting GPU 1 to GPU 10,000 is slow, the whole system just grinds to a halt.
And there's a war going on here, right? Between two technologies, the gold standard and the people's champion.
That's a good way to put it. In the high-end corner, you've got InfiniBand. It's the Ferrari. Proprietary, expensive, ultra-low latency. It was built purely for this.
And the challenger.
RoCE V2.
Yep.
Which is basically Ethernet.
Ethernet, like
Wow.
a cable I plug into my router at home.
The very same. Well, a supercharged version of it. The big advantage of Ethernet is that everyone knows it, it's cheaper, but it needs constant tuning. If you don't manage the traffic just right, you get data jams.
But the report suggests this whole war might be becoming irrelevant because of light.
Yes. Silicon photonics. This is Spectrum X. We're just hitting the physical limits of pushing electrons through copper wires. Too much resistance, too much heat. So now we're starting to use optical fibers right down to the chip level.
So the data is actually traveling as light.
Exactly. It boosts energy efficiency by 5 times, and it just blurs the line between a physical box and the network. To the software, a data center with 100,000 GPUs. It doesn't look like a cluster anymore. It just looks like one single massive brain.
Which brings us to the next problem. You have this massive brain. What are you going to feed it? Layer 3. The fuel. The data.
And this is where I think the real panic set in around 2025.
The report says the internet was mined out. Now, I have to push back on that. I go online, there's millions of new posts every single day. How can we be out of data?
We aren't out of data. We're out of quality data. Sure, there's an infinite supply of TikTok comments and cat memes, but that's not what teaches a model logic or reasoning. We need textbooks, scientific papers, high-quality journalism, and we basically used it all up.
So we fed the AI the entire library of human knowledge, and we ran out of books.
Essentially, yes. So the industry had to pivot. If you can't find more human data, you have to make it. And that's where synthetic data generation comes in.
Robots teaching robots.
It sounds circular, but it's this really sophisticated loop. They call it generate critique filter. You take a huge smart model like a GPT-4o and ask it to write a textbook on, say, quantum physics. Then you have another model grade that textbook.
Like a teacher grading a student's paper.
Exactly. If the synthetic textbook gets an A+, it goes into the training set for a new, smaller model. If it gets a C, you just delete it. We're effectively synthesizing a curriculum.
But isn't there a risk there? If the AI gets something wrong, and then it teaches another AI that wrong thing, don't you get this kind of magnification of errors, like inbreeding?
That is the single biggest risk. They call it model collapse. But there's another, more immediate issue the report flags: decontamination.
Which sounds like we're cleaning up a virus or something.
In a way, you are. The virus is the answer key. If you train an AI on the whole internet, it might have accidentally seen the questions and the answers to the benchmark tests we use to measure its intelligence, like GSM-8K.
Oh, I see. So the AI isn't actually learning how to do math. It's just memorizing the answer to question number 4.
Precisely. It's cheating. So engineers have to spend a huge amount of time scrubbing all the data to make sure the AI has never, ever seen the test before.
Okay, so we've got the hardware, the network, the synthetic fuel. Now let's look at the anatomy of the brain itself. Layer 4, architecture.
This is the big shift from dense models to MOE mixture of experts.
This one makes sense to me intuitively. The old models were dense, which means what exactly?
It means every time you asked a question, the entire neural network fired up. Imagine a doctor trying to be a GP, a cardiologist, a neurologist, and a podiatrist all at the same time. Every single patient gets the full brain power of this one exhausted doctor. It's incredibly inefficient.
And expensive, I'm guessing.
Extremely. So we move to mixture of experts. Instead of one generalist Think of a hospital with different departments. You have a router at the front desk.
The traffic cop.
Right. You ask a question about the French Revolution? The router sees that and sends you straight to the history expert, the math expert, and the coding expert. They don't even wake up.
So you get the intelligence of a massive trillion-parameter model, but you only pay the energy costs of a much smaller one.
Exactly. It's the only way we could scale up without bankrupting everyone.
Now, in this layer, the report mentions a piece of software called Triton. It's a compiler from OpenAI. Why does a compiler get a specific call-out in a huge report like this?
Because this is a huge deal for the business side of things. For a decade, NVIDIA's dominance wasn't just their chips, it was CDIA.
Their coding language.
Right. And it was notoriously difficult to learn. If you wanted your code to run fast, you had to write in CUA. That locked everyone into NVIDIA. But Triton changes the game. It lets a developer write in Python, which everyone knows, and Triton automatically translates it into incredibly efficient code for the GPU.
So it just lowers the barrier to entry.
It demolishes the moat. It democratizes high-performance programming. All of a sudden, you don't need a PhD in hardware architecture to get every last drop of performance out of a chip.
That leads perfectly into layer 5, optimization. Because we aren't just running these things in data centers anymore. We need them on our phones, our laptops.
Right, the deployment problem. You cannot fit a 405 billion parameter model on an iPhone. The memory just isn't there. So we use distillation.
The teacher and the student again.
Yep. You take that massive teacher model and you have it teach a tiny, compact student model. And the goal is for the student to learn the logic behind the answers, not just memorize the facts.
And once you have that small model, you shrink it even further.
You compress it. This is called quantization.
Explain that for me.
So computers store numbers with a certain amount of precision. Usually, a weight in a neural net is stored with, say, 16 decimal places. That takes up space. Quantization basically asks, do we really need all 16 decimal places, or is 4 good enough?
It's like rounding down. But doesn't that make the model dumber?
It used to. If you just chopped off the decimal point, yeah, the model would get brain damage.
Yeah.
But now we have something called AWQ, activation-aware quantization.
Fancy name.
It's brilliant. The algorithm analyzes the whole network and figures out which weights are the important ones, the ones that carry the most intelligence. It protects those. Then it ruthlessly compresses all the less important ones. It's like zipping a file, but being super careful not to blur the faces in the photo.
So we have a compressed, distilled brain. Okay, now, layer 6. The application. What is this brain actually doing?
Well, it's not chatting. If there's one takeaway for you listening, it's this. The era of chat is dead. We are in the era of agents.
Agentic workflows.
Right. A chatbot is passive. It waits for you to talk to it. An agent has a goal. You give it a mission. Plan a trip to Tokyo and book the flights. The agent breaks that down into steps. It uses tools. It searches the web. And it executes.
The report had that great example of a team of agents. One's a researcher, one's a fact-checker, one's a writer.
It's a virtual workforce.
Yeah.
And crucially, they don't hallucinate as much anymore because of our RAG retrieval augmented generation.
The open book test.
Exactly. Instead of just relying on its own shaky memory, the AI can access a vector database using tech like scan and search billions of real documents. It finds the facts, reads them, and then it answers you. It grounds the AI in reality.
Okay, so let's zoom all the way out. We have liquid-cooled supercomputers running these agentic swarms that can act autonomously. That is incredibly powerful and, frankly, a little terrifying. Which brings us to the final layer, governance.
The rules of the road, and this is where the story gets really complicated.
Yeah, the report highlights a massive split in the world, a real divergence between the European Union and the United States.
It's like two different realities. The EU has gone all in on the risk-based approach with their AI Act.
This is the safety-first model.
Strict safety. They've banned what they call unacceptable risks, things like social scoring or emotion recognition at work. If you're deploying Gen AI in Europe, the transparency requirements are massive. You have to prove it's safe before you can turn it on.
Yeah, and then in the U.S., the report specifies the Trump administration late 2025.
Total opposite direction. The philosophy there is innovation first, or maybe competition first is more accurate.
Trying to beat China.
That's the driving force.
Yeah.
The report mentions an executive order that actually blocks individual states from making their own AI safety laws.
So that California safety bill that everyone was debating.
Gone, preempted by federal law. The U.S. stance is all about deregulation, energy dominance, and AI export. They view AI as a national weapon. And you don't regulate a weapon so hard that you can't build it. You build it fast so you have more than the other guy.
It's a fascinating and really high-stakes global experiment. One half of the Western world is prioritizing rights and safety. The other is all in on speed and scale.
And we won't know who is right for another decade. If something goes wrong, the EU will look like geniuses. If nothing goes wrong and the US economy just skyrockets, Europe's going to look like a museum.
Speaking of the future, let's wrap this up. The report looks ahead to 2030. What's on the horizon?
Three things really stood out to me. First, the AIOS, operating systems with souls.
Which means what?
It means the AI isn't just an app you click on, it is the computer. It knows every file you have, every email, every single keystroke. It anticipates what you need before you even ask. Deep integration.
Okay, second.
Physical AI.
Yeah.
Robots. But not the clunky ones we're used to seeing. The report uses this weird phrase, elf-like dexterity.
Elf-like
So
dexterity.
it implies grace, you know?
Yeah.
We're feeding these world models to robots so they understand physics intuitively. They aren't programmed to move. They learn to move.
And the third thing.
Optical computing. We talked about using light for networking. By 2030, we might be using light for the calculation itself, moving away from electricity for inference. It might be the only way to solve that energy crisis we talked about way back in Layer 1.
Before we go, I want to touch on the final provocation from the notes. You wrote down alignment cost. What does that mean?
It's a philosophical problem we're starting to see in the data. We spend so much time making these models polite, safe, and obedient. We align them with our values.
Which is a good thing. I don't want a racist chatbot.
It is good, but the data is starting to suggest there's a tax. The more we align them, the less creative they seem to become. The safer we make them, the less likely they are to have those spark moments of true genius.
So we might be, what, lobotomizing our greatest invention out of fear?
We might be. And here's the kicker. The report predicts that by 2027, AI will start automating its own research. It'll be designing the next chip. It'll be writing the next algorithm.
Self-evolution.
And if that happens, the AI might look at our safety alignment as just an inefficiency to be optimized away. And then the question becomes, what is the role of the human engineer? Are we the pilots anymore? Or are we just the biological bootloader that got the whole thing started?
That is a heavy thought to end on. Next time I open my laptop, I'm going to look at it very differently. It's not just a screen. It's the tip of a very hot, very liquid-cooled, and very legislated iceberg.
Just don't drop it in the bathtub trying to replicate immersion cooling.
I will try to resist the urge. That's it for this deep dive into the 2026 AI stack. Thanks for listening, and we'll catch you on the next one.
See you then.